In this video, we're going to look at finding the area bounded by f of x equals 64 minus x cubed, the x-axis, and the vertical lines x equals 1 and x equals 4. And we're going to use a Riemann sum here. So we can do this with a lower and an upper sum, and that's like a lot of work. So we're going to use a Riemann sum that allows us to pick any point in a partition to be the height of a rectangle. For convenience, what we're going to do is we're going to use a uniform partition. So we're going to pick the widths of our rectangles, delta x, to be the difference between the endpoints, and we're going to divide that up into n equal parts. Okay. So it's going to be 3 over n is going to be the width of each rectangle. And this is going to partition our interval 1 to 4. Okay. And this is a uniform partition because everything's of the same length. And we're going to use the right endpoints because that's easier to use typically than the left endpoints. Well, I guess it depends on what we use for our index. So. For our endpoints here. So what I got to do is, I got to start at 1, and then I got to start adding 3 over n's all the way until I get to 3. And so we don't want to start at 0. We need to start at a, whatever a is. In this case, it's going to be 1. So we need to slide to the right 1 unit. So, and then this is just going to be our how many 3 over n's are we going to add? So if we write that here, that's going to be 1 plus 3I over n, and that's going to be what we plug into our function to determine the height of each rectangle. And so the area of a rectangle is going to be, we're going to plug in these 1 plus 3I over n. That's going to give us the right endpoints, and then 3 over n. That's going to give us the width. So here we have the width, and this is the height of each rectangle. Okay. So when we're going to do a Riemann sum, it's going to be a limit. So the total area is going to be defined to be the limit as n goes to infinity. This, and we're using a little bit nicer partition, so it's not necessarily the norm going to 0. It is going to 0, but we have a more concrete partition here of I equals 1 to n, and then f of 1 plus 3I over n times 3 over n. Now in the in the summation, the 3 over n, that's not moving. So what we're going to do is we're going to factor out. We can't factor it out of the limit because the limit involves n. So there we are. And when we plug in 1 plus 3I over n, it becomes 64 minus 1 plus 3I over n quantity cubed. What we're going to need to do is we're going to need to expand this out. So we're going to have to multiply that all out. So we have limit as n goes to infinity, 3 over n, sum I equals 1 to n of 64. And we're going to go ahead and expand that. So it's going to be minus 1 plus 3 times 3I over n to the first power plus 3 times 3I over n squared, and then plus 3I over n cubed. And that's just using our binomial theorem, okay? And so we're obviously out of room. This one has a lot of stuff going on. So we're going to go on to the next slide. And there it is again, okay? Now we're going to go ahead and apply our formulas. So we have formulas for I, formulas for I squared, and formulas for I cubed. So what we're going to do is we're going to go ahead and apply those formulas in the summation. Okay, so if I add up 64 n times, I got 64 n's. minus adding 1 up n times. It's going to be n, but we're subtracting it, so it's minus n. Okay, then you got 3 times 3, so we're going to have 9 over n, and then adding up the i's is n plus 1 over 2. The next piece, you have 3 squared, so you got 3 times 9, which is going to be 27, divided by n squared. Formula for I squared is n plus 1, and 2n plus 1 all over 6. And then finally minus 3 to the third power is 27 divided by n cubed. And then the formula for I cubes is n squared, n plus 1 squared. Barely fit it in there, all over 4. Okay. So what we're going to do now is we're going to distribute this 3 over n all the way through, and also expand out and do some simplification. So, you know, we are lacking real estate, so we're going to try to be efficient here. Okay, so limit as n goes to infinity, and the 64 minus n, 64n minus n is going to be 63n, and then when we multiply it by 3n, the n's are going to cancel, and you have 63 times 3, which is 189. For the next piece, we're going to cancel those n's out there, just because they're easy to cancel out. And 3 times 9 is 27, and then when we expand this out, it's going to give us n and a plus 1, multiply the 27 through, all over 2n, and then that piece is going to be 81 over 6n cubed. So what happens here is, what do we got here? This n will knock out one of those n's there. Oh, I didn't do that. I didn't do that simplification. That's okay. So I just went as straight ahead and did n times n squared, which is n cubed. 3 times 27 is 81, all over 6. Yes, I can reduce, but I chose not to here. There's a lot going on. Then we'll go ahead and we'll expand all of this out. So we're going to multiply that all out. That gives us 2n cubed plus 3n squared, and then plus just n. And then the last piece, I did do a little bit canceling. So I took the n squared that knocked out 2 of the n's on the bottom here, and then we multiply it by this n here, and that's going to give us an n squared. 3 times 27 is 81, and then you got the 4 on the bottom. FOIL out the n plus 1 squared, that's n squared plus 2n plus 1. Alright, so limit of 189, it's just 189. Okay, now what we got going on here is this part right here, that's going to go to 0. But you have 27n over 2n, so the n's are going to drop out, and you'll be left with 27 over 2, minus 27 over 2. Okay. Then over here on the green portion here, these have exponents smaller than the n cubed, so as n goes to infinity, they're going to go to 0. The only one that matters is these n cubes are the same, so what we'll have is 81 times 2, which is 162 over 6, which is going to be left over when we take that limit. Okay, and then finally, same argument here, these degrees are less than the n squared, so they're going to go to 0. So the only thing that matters is the 81 over 4, and that's what's going to end up here, minus 81 over 4. And put that in your calculator, and we get the area to be 128.25. And that's using our Riemann sums. You can do a lower and upper sums, but it's a lot more work, especially if you want to use the left endpoints for doing the upper sums. You'd have an I minus 1 to the third power, and that's even more cumbersome to expand out. So that's how it is, and we'll get a little bit more appreciation from the fundamental theorem of calculus. Will make things like this a little bit easier.